Okay, all right, let's pick up again where we stopped. And let's see. So, filters, how do we use inductors and capacitors? Well, we're going to use their behavior at low and high frequencies, and we'll model them. This is a quick analysis technique where we can model inductors and capacitors as either open or closed circuit. Okay, open circuit or closed circuit. And I'll show you what I mean. So, a inductor's impedance ZL is J 2 pi FL. So as the frequency increases, the impedance of the inductor also increases. Okay, as frequency increases, ZL also increases. As frequency decreases, ZL decreases. Because think about it. Chapter 3, what did we learn? Inductors store energy in the magnetic field. Once the magnetic field is maximized, meaning it has stored all the energy it is capable of storing, it behaves like a short circuit wire, right? Inductor is just a short circuit wire. So once the magnetic field is full, energy storage is full, inductor behaves like a short circuit until you start to change the input. When you change the input, inductor reactance will oppose any change in that input. And so the faster it changes, meaning as frequency increases, the faster it opposes any change in that input, which makes sense. So this is the quantitative illustration based on the equation, and the other is the qualitative explanation, what is happening. The faster the input changes, the more the magnetic field opposes any change in that input. And because of this, we can model the inductor as a short circuit at extremely low frequencies and as an open circuit at extremely high frequencies. So if F goes to 0, ZL is 0, right? F is 0, ZL is 0. And as F tends towards infinity, ZL also tends towards infinity, meaning it is open circuit. Make sense? ZC, on the other hand, is the exact opposite. You have 1 over J 2 pi FC. As the frequency increases, ZC decreases. And as the frequency decreases, ZC increases, inversely proportional. Capacitor behaves like a short circuit for DC. I'm sorry, open circuit for DC. Remember, capacitor stores charge in an electric field. When it reaches full charge, electrons stop flowing through the circuit. It behaves like an open circuit. If you now change the input, meaning the charge is reversed, then electrons start flowing again, meaning there's current present in the circuit again. And so the faster it changes, the more current would flow. So as frequency tends towards 0, capacitor behaves like an open circuit. You can model it as a open circuit. And as as frequency tends towards infinity, capacitor impedance tends towards 0, we can model it as a short circuit. So when we say open circuit and short circuit, open circuit would simply be modeled by a break, and short circuit by a wire. Okay, simply replace, if it's open circuit, we remove the component. If it's short circuit, we replace it with a wire. And this is how we're going to model the capacitor and inductor, and then quickly analyze the circuit. Okay, so we'll put everything together in the next few slides. But let's take a pause and think over that. Let me know if you have any questions. Any questions from anyone? Okay. So based on these, we have a 2x2 matrix. We have a capacitor that can be used to make two kinds of filters, low pass and high pass, depending on which range of frequency it is allowing to pass. And we can take an inductor and make the same two filters, low pass and high pass. And then we can combine those to form a band pass or a band reject filter. Okay, band pass or a band reject filter. Chapter 4, if you have one energy storage component in a circuit, you have a first order differential equation. You have what is known as a first order circuit. So it is one component. It's a first order filter. Actually, let me write it here. And if you have two components, it's a second order filter. And of course, circuits are never without resistors. And so a capacitor filter would be RC filter. Inductor filter would be RL filter. So I'm going to go over all four kinds of filters, but I will show you that they're exactly the same circuit. Okay. This is a series circuit. The terminals are simply known as the measurement terminals or the output port, a series circuit, right? There is no component connected at this junction up top. So this is a RC circuit, and I'm going to redraw this so that the series connection is evident. Okay. Taking the output across the capacitor, and this is your input V in. Make sense? Right? This is your R, and this is your C. Taking the output across the capacitor. It's a series circuit. There is no other component connected to either the resistor or the capacitor. Even though it seems as if there are three connections at that node right here, there are not three components. There's only two components. So please keep that in mind. Okay, there's only two components. So it's a series circuit and taking the output across the capacitor. So let's model this circuit. If F is equal to 0 hertz, what happens? Capacitor behaves like a open circuit. So capacitor behaves like an open circuit. So it's replaced with an open circuit. And your circuit simply becomes like this. You have your output. Does this circuit look familiar? It's kind of like the Thevenin equivalent circuit. Your capacitor is open circuit. You only have the resistor in there. What is V out? V out is simply equal to V in. Okay, so low frequencies, we are able to collect output. Let's take a pause. If you have low frequencies coming in at the input terminals, capacitor behaves like an open circuit, and we are able to obtain V out across that capacitor. In terms of circuit analysis, you could think it this way. V in is applied to the capacitor through a resistor R. When it first begins charging, current is flowing through the resistor, electrons are flowing through the circuit, capacitor is building up the charge. Once it reaches V in, meaning the voltage across the capacitor reaches a level of V in, both ends of the circuit are at the same level, there is no more charge imbalance. Hence, the electrons stop flowing. If the electrons stop flowing, meaning the current through the resistor and to the rest of the circuit is now zero, capacitor is at V in. The voltage across the capacitor reaches the level of V in. Make sense? I would say in this chapter, do not get too bogged down into the circuit analysis. Okay, you want to take a step back and analyze it as a sealed box. Okay, this is just to show you the operation of basic filter circuits. Okay, if you have V in, the frequency for V in is low, output would be equal to V in. On the other hand, if frequency goes high, if it tends towards infinity, capacitor is replaced with a short circuit. So what is our output in that case? Capacitor is replaced with a short circuit wire. What happens when these two nodes are connected together? What is the voltage output across those two nodes? The short circuit wire is the same node. If you measure voltage at the same node, what is it that you're measuring? Zero volts. Output drops to zero, right? It's the exact same node. They are connected together. It's like a short circuit wire. So V out is equal to zero. V out is equal to zero means output is being blocked. Output is being blocked. Okay. And so this functions as a low pass filter. High frequencies are blocked. Low frequencies are passed through. Blocked meaning output goes to zero. 0 volts or close to 0 volts. So this circuit functions as a low pass filter. All right, let's take a 10-second pause. Let me know if you have any questions. Any questions? Okay. Then let me show you what happens if you take the same circuit and you take the output across the resistor. So it is still the exact same circuit. The positions of capacitor and resistor are switched, but effectively it's still the same circuit. So now, as F tends towards zero, capacitor is still behaving like a open circuit. This time the output is across the resistor. So V out goes to 0. Low frequencies are blocked. As F tends towards infinity, capacitor behaves like a short circuit. And so V out is equal to V in. High frequencies are passed. And therefore, this works as a high pass filter. This is the same circuit. Okay, same circuit as the low pass filter. There's no difference whatsoever. You're simply changing the output terminals. That is it. We are not changing anything else about the circuit. Okay, it's exactly the same circuit. Okay, questions? Okay, then let's talk about the frequency response charts. So first order low pass filter, I'm going to draw a simple chart in terms of frequency and voltage. So it's now frequency in hertz on the y-axis and V out on the x-axis. If it's a low pass filter, low frequencies are passed through, and higher frequencies are blocked. But it is not an ideal filter, right? There is no sharp drop off. This is known as FB or FC. The B stands for break. C stands for cutoff frequency. As engineers, you should be familiar with both terms. FB stands for break frequency. FC is the cutoff frequency. That is the frequency that demarcates the line, the border between the pass band and the block band. Okay, pass band and the block band. In real life, there is no sharp drop. Okay, filter design is a specialization within EE itself. Okay, it's an entire specialization. So filter design, you can have first order, second order, third order, higher order filters. There are trade-offs that can try to approximate the sharp drop off. Okay, but in real life, there's never a sharp drop off. That is always a curve. And if you see to the left of this pass band, there are certain frequencies. Basically, these frequencies that are blocked in the sense that their V out level has dropped. It's not 100%. So if this is the level of V in, at V out should be equal to V in below the break frequency or below the cutoff frequency. And here you have the shaded area, not shaded, sorry, to the right. These frequencies are blocked, yet there are certain amount of frequencies that are passed. Passed in the sense the voltage level is not quite zero. Does that make sense? Man, it's a lot of information to get our brains trained. So far, we've always looked at signals with time on the x-axis. Now we have frequency responses, frequency on the x-axis, and we are seeing how the output voltage behaves in response to the different frequencies coming in at the input. So this is a frequency response characteristic of a low pass filter. It's showing you how the output voltage changes as a function of the input frequency. An ideal low pass filter would allow all frequencies up until the cutoff frequencies to pass through because they are lower than the cutoff frequency. And then once the cutoff frequency is crossed, the output voltage level should drop to zero. In real life, the filter performance does not work exactly like a sharp square or sharp rectangle. It's always a gentle slope. So there is an area before the cutoff frequency that loses a certain amount of voltage, and there is a certain area of the graph after the cutoff frequency that is still passed through. So when circuit designers are building these kind of circuits, they have to account for the fact. Meaning, if the incoming signal is, let's say, 5 volts, for instance, what do you consider as an engineer? What would you consider as cutoff level, and what would you consider as pass level? Meaning, if the level falls below 4 volts, even if it's 3.5 volts, you still obtain an output, but you would consider that as being cut off, meaning the system should stop responding if the input or the output is 3.5 volts. Think on that and let me know if you have any questions. Does that make sense? Hopefully. Let's take a longer pause. Any questions before I move on? Okay. So there are some equations for the transfer function and the break frequency. The break frequency is actually not this one. Let's go here. Break frequency is a constant and it depends on the values of the resistor and the capacitor. FB for a RC circuit is always 1 over 2 pi RC. Transfer function magnitude is also not a constant, but it depends on incoming frequency F. So H of F is 1 over 1 plus J F or FB. Okay. And this is the exact same circuit. So when you go and change the output across the resistor, these still remain exactly the same. Sorry, not this one. This one. FB remains exactly the same. 1 over 2 pi RC because the components haven't changed. The function has changed from low pass to high pass. So the high pass transfer function is listed here. Okay. Then let's look at a RL low pass. For an inductor, as frequency increases, ZL increases. And so inductor is modeled as an open circuit. So at high frequencies, if you take the output across the resistor in a RL circuit, V out goes to 0 volts. As frequency decreases, ZL decreases, and inductor behaves like a short circuit. And so V out is equal to V in. V out is equal to V in. And so this works as a high pass. This works as a low pass filter. So low frequencies, V out is equal to V in. High frequencies, V out is equal to 0. And so it works as a low pass filter. The break frequency equation is different. So it's R over 2 pi L. Capacitor is 1 over 2 pi RC. Now, what if we combine all of these together? If we combine all of these together, we get what is known as a resonant circuit. A resonant circuit. So we had a RL filter. And we had a capacitor. Right? So this is L, R, and C. VS or VN, doesn't matter. So it's a series RL filter, or it could be considered as a series RC filter. You combine all of it together. What kind of filter do you expect? Band pass or band reject? Okay, you can get a band pass or a band reject filter. The reason it is known as a resonant circuit is because there is energy transfer that takes place between the two components. Remember, I drew this diagram a little bit earlier, where in the positive half cycle, energy flows into the inductor. Negative half cycle, it flows out. In a capacitor, energy flows in the negative half cycle and flows out in the positive half cycle. So if you have both these components together in a circuit, when energy flows out of the inductor, it flows into the capacitor. And when energy flows out of the capacitor, it goes into the inductor. So there is energy exchange taking place. And due to this, voltages and currents that are larger than the input source could appear in the circuit. Okay. And that phenomenon takes place only at one single frequency, and that frequency is known as the resonant frequency. And the phenomenon is known as electrical resonance. Electrical resonance. If you are taking the lab, you would be able to see this phenomenon in the lab, where the voltage across one of the components would be larger than your source voltage. And the reason is because energy is stored in the inductor, energy is stored in the capacitor. The stored energy plus the incoming Vs gives rise to a larger voltage. Does that make sense as a concept? Okay. So let's talk about, I will leave the equations and everything for next class, but I want to talk about like a real life application. So let's see. What does this remind you of? I just heard one murmuring, nothing from online students. If this is not familiar, I think you all need to go out a little bit more on the weekends. You know what they say about engineers? We work hard, we study hard, and we also party hard. Or maybe it was only in my day. You guys are probably more studious than I was.
We party the hardest.
All right. Sorry, what?
We party the hardest.
Okay, so this is a speaker box, and each one of these individual speaker drivers that you see inside, they are known as speaker drivers or just as drivers. So what is this one called? The small one? Tweeter. This one? Anyone? Woof, woof. This is the mid-range. So mid-range, tweeter, and woofer. There is a physical reason why the woofer is large, okay? Woofer reproduces the low frequency spectrum of the audio signals, which is basically a thumping bass sounds, like deep voices, explosions, blasts in movies, or thumping bass sounds that is reproduced by woofers. Low frequencies, wavelength is inversely proportional to frequency. So as higher, it requires a bigger surface because it needs to move a lot of air to reproduce that sound, okay? And so physically, it requires a larger surface area. Hence, woofers reproduce low frequencies. Tweeters, on the other hand, reproduce the higher frequencies. And mid-range, well, anything that falls in the middle, especially like vocals, are reproduced by the mid-range. Typically, most speakers are two-way speakers. So this is known as a three-way speaker box, because there are three different paths, right? Three different drivers in there. Even tiny speakers that you see around the room here would have two drivers inside it. One would be like a woofer to handle the low frequencies. One would be like a very small tweeter to handle the high frequencies. So even a small computer speaker might have like two speaker drivers inside it. So there would be two-way speakers. If you look at the back of this big speaker box, you would see something like this. This is like enlarged. You have two connections, one red, one black. And you'd have a speaker wire. And so you can see speaker wires dangling from the top of these connections right here. Okay, each one of those has two wires. It goes into, so your signal coming from your amplifier goes in, right? It's a pair of wires, two wires coming in. It goes inside the box where the magic happens. If you open up this connector jack, which is not that big, and usually only has 2 screws, and you remove it, you will see that internally the connection is going to a circuit box, and that circuit box might have a huge coil or 2, might have big cylinders, which are capacitors, and then resistors, some sort of resistors in there. Okay. And this incoming signal is split into 3. One goes to the tweeter, one goes to the woofer, and the other one goes to the mid-range. So 2 pairs of wires, signals are now split into 6 wires, or basically 1 input port and 3 output ports. Okay. And what it is doing is, this is an electronic filter that is diverting the low frequencies to the woofer, the higher frequencies to the tweeter, and the middle range to the mid-range speaker. This is known as a crossover network. Okay, this filter is known as a crossover network inside the speaker. Even the cheapest of speakers will have a filter inside it. It's very easy to build. We saw this right here. Inductors are slightly more expensive than a capacitor, but a capacitor is very, very cheap, costs a few cents. And I swear, you know, I've seen the cheapest ones, the cheapest speakers that you can find, literally do not even have a circuit board on there. They'll simply have a resistor and a capacitor like tied together, some solder on it, and they'll stick it directly on top of the speaker terminals itself. So you have, this is where the input comes in, and V out is taken across the resistor and simply stuck onto the speaker. Costs a few cents, that's it. And so I've seen that too. Anyway, this crossover network is nothing but our series RLC network, series RLC connector. If you take the output across the capacitor, what do you get? You get the low pass filtering, right? RC circuit, you get a low pass filter option. If you take the output across the resistor, you get the high pass output. And if you take the output across the resistor, is where you would obtain the band of frequencies that are blocked by the high pass and the low pass connection, and the middle band of frequencies that are allowed to pass through, which is what you obtain across that resistor. So I just wanted to show you this real life example, and then we'll end class here today, and we'll pick up here again on Monday. The homework for the transfer function is not due until tomorrow, but I would strongly recommend or strongly suggest you get it done today itself. There's only 1 or 2 problems on there, and they're both very similar to the example I solved in class. So while the material is fresh, go ahead and finish that off. And then the resonance circuits homework will be due next week. So not until then. All right, questions? Any questions? There's a lot of information to go through. So go ahead and get that done. Review it. Reach out to me if you have any questions. I'll be available over the weekend also. But we will end class here today, and I will see you all on Monday. Or unless you're taking the lab, I'll see you in just a few minutes then. All right. Okay, any